Hello my beautiful students, I guess you people are preparing well for your PU2 examination. So welcome back to a new session, and this particular video is going to be a treasure hunt for you. Why? Because let's imagine you are studying so much, you are going through so many questions, you are practicing, but what if in a single video I kind of leak the question paper? Yes, all possible question that you are going to face in your PU2 examination is going to be covered in this single video. All the 2 markers and 3 marker question that from all the chapters throughout the chemistry is going to be covered in this single video with a proper explanation. So without further delay, let's start with our session. Please watch till end and make sure you are making proper note of this question. So without further delay, let's get started. So before starting, just let me tell you that Deeksha Karnataka channel has launched the most awaited series, that is a ABHYAS series for the KCET examination. If you are preparing for KCET along with your PU examination, without further delay, please enroll yourself in this test series. That's gonna help you to get top 1000 rank in Karnataka in your KCET exam, because that's going to provide you 35 mock tests along with the previous year questions of the all chapters and so many benefits, and very less price you are going to get this deal. So without further delay, enroll yourself to make your preparation better in KCET as well. Okay, so let's proceed with solution chapter. Please be assured that these are short question. You are going to face the question from here only. Yes, so first question is state Henry's law, write the mathematical form. So here you can see I have mentioned the year. So many years this type of questions are repeated. So you can see directly you can write that it states that at constant temperature the solubility is directly proportional to the pressure, partial pressure of the gas. Okay, and definitely whenever you are writing the mathematical abbreviation, please make sure that you are writing the abbreviation of each terminologies, like what is K, what is X, and what is P. I guess it's clear to you. Let's proceed further. Give any 3 application of Henry's law. Very important question, repeated question. So here you can see first you can just take the example of like carbonated beverages, where with a high pressure the carbon dioxide gas gets dissolved. Second, you can take the example of the bends that scuba diver used to face. So basically what happens when the pressure increases, water pressure increases, then in your blood, like scuba divers used to carry the oxygen tank, right? In that nitrogen gas is also there. So whenever the pressure increases, then nitrogen gas gets entered, the solubility of nitrogen increases in your blood, in the scuba diver's blood, right? And whenever they come out from the depth of the ocean to the surface, then what happens, that particular nitrogen gas comes out in a form of bubble because pressure is decreasing, right? And it's a very painful situation, and that is called as bend. Okay, and to prevent this phenomenon, now they mix helium along with the nitrogen in that particular cylinder, so that the solubility of nitrogen decreases in presence of helium. Yes, another point that you can mention, that is about the anoxia. So whenever you are going to the higher altitude, what happens, the partial pressure of the air decreases. As a result of this, brain gets lesser oxygen supply because oxygen doesn't get dissolved. Solubility of oxygen in the blood reduces as well. As a result of this, what happens, the thinking power decreases, and so many medical conditions arises, and that's called actually anoxia. So that also can be explained with respect to Henry's law. I guess it's clear to you. Next you can proceed with the question, that is difference between ideal and non-ideal solution. So here comes the differences. Any 2 or any 3 you can remember for the 2 marker questions. So definitely they obey Raoult law, they do not obey Raoult law. Delta V mix, delta H mix, both of them for ideal solution is 0, for them it's not equals to 0. And most importantly, for the ideal solution, the interaction between AA and BB is equals to the interaction between AB, right? And for those cases, the interaction is not similar, okay? So these are some characteristics. Some example also you can see the homologous series compounds like let's say N-heptane and N-hexane. They are the example of the ideal solution. Non-ideal solution, you can take the example of chloroform and acetone. Okay, this type of thing you can take. What are azeotrope or azeotropic mixture? Give an example. So here you can see this is basically a binary liquid mixture. They are having same composition in the liquid phase and in the vapor phase as well. So here comes few example. You can see 95% ethyl alcohol along with that 5% water. Okay, so these are some examples of the azeotropic mixture. So next you can see component of a non-ideal binary solution cannot be separated by fractional distillation. Why? So basically they forms azeotropic mixture. That's the reason they cannot be separable. That's simple answer. Next you can see give reason for the following. First is raw mangoes shrivel when pickled in brine solution. Okay, so you can see one by one, whenever any kind of raw mango it is shriveled, like it is pickled in the brine, then what happens? Exoosmosis takes place, right? So as a result of this, water molecules of mango that enters into the brine solution, as a result of this that gets shriveled, right? Next is blood cell collapse when suspended in saline solution. What happens? Here also exoosmosis takes place, and the water molecule from the blood cell, it basically enters into the, it comes out from that and it enters into the saline solution. Next, wilted flowers revive when placed in fresh water. So basically this is the scenario of endosmosis. From the outside itself the water comes inside, okay? The water molecules enters into the flower. Okay, so that are the questions. I guess it's clear. So now here comes one point. What is brine solution? So brine solution is basically 0.9% saturated aqueous solution of sodium chloride is called brine solution, and 0.9% NaCl is called saline. Okay, let's process what is reverse osmosis. Very important question, and give one important application of it. So as you know, the osmosis process means whenever the solvent molecule from the lower concentration zone to higher concentration zone, it travels through a semi-permeable membrane, right? That is called normal osmosis. So what is reverse? Definitely the process, if you just reverse it by putting some pressure more than that of osmotic pressure, right? So what basically will happen here? Here from higher concentration zone to lower concentration zone, the solvent molecule will pass through a semi-permeable membrane. How? If you are putting some extra pressure more than that of the osmotic pressure, then the reverse osmosis will take place. So using these particular process, the desalination of the sea water can be done. Okay, just go through this once. I guess it's clear. So that's all about the 2 marker question from the solution chapter. Numerical problems are also there. Definitely we will come back to it. So here you can see electrochemistry. So from electrochemistry, one of the most important question, it is about the Sol bridge. So Sol bridge, it is basically one U-shaped glass that is filled up with the agar-agar gel that contains KCl, KNO3, NH4NO3, this type of salt. Okay, let's proceed. What is the role of Sol bridge in the connecting anode and cathode or 2 half cells? So very important question. First, it maintains the electrical neutrality for both sides. It prevents liquid-liquid junction potential. What is liquid junction potential? Let's say I am not taking 2 different containers. For the galvanic cell, what happens? I take 2 half cell, right? 2 different container. Let's not take 2 half cell. Let's just mix all those solution. Let's say zinc sulfate and copper sulfate we mixed. So what happens? In one solution negative potential will be created, in another solution positive potential will be created, and that will create one junction potential. Two liquid junction potential will be created. Okay, so for that cell potential will be lost. Right, we will be losing this overall cell potential, right? So in order to prevent this, let's make 2 different half cell and connect them using a U-shaped tube, that is your salt bridge. Next you can see it can prevent the accumulation of the charge in the half cell. Okay, so if somewhere let's say more charge is there, somewhere it is less charge is there, so definitely K plus Cl minus inside the agar gel, they can be like their transport number is equal, so they can transfer from here to there wherever it is needed. They can travel and they can minimize or prevent the accumulation of extra charges. Let's proceed. What are inert electrodes? Gives example. So basically inert electrodes are those electrodes who doesn't take part in the reaction, but it provides the surface area for the redox reaction. They are called inert electrodes. Some example you can take it as platinum electrode, like gold electrode. Okay, they just provide the surface area. Let's proceed. Define limiting molar conductivity. So limiting molar conductivity is a very, very important concept. So basically we know from the Debye-Huckel graph, Debye-Huckel equation, we can plot a graph for the strong electrolyte, okay, where we can plot molar conductivity versus root of concentration graph, right? And if you just plot the graph, the nature will be something like this. Let's say I am having KCl, okay, let's say here I am having lambda m and here I am having root C. Okay, I will get this type of graph. Okay, so what it says that if you decrease the concentration, molar conductivity will increase. If you decrease the concentration, molar conductivity will increase, but not a sharp increase for strong electrolyte. Okay, so now if I just extrapolate this graph, then it will cut the lambda m axis here, and this particular point is basically the intercept, and that is called as lambda m infinity, or limiting molar conductivity. Okay, so what is the speciality here? So here at this point the concentration is almost 0, right? It's a hypothetical concept. Whenever you are diluting a solution infinitely, whenever you are diluting the solution infinitely, whatever the molar conductivity you will get, that is called limiting molar conductivity. So hypothetical concept, in reality you will not get it, hence you have to plot a graph like that, and then you have to extrapolate that, and then you will get the limiting molar conductivity. And it is only and only possible for the strong electrolyte only. For weak electrolyte, limiting molar conductivity calculation is a little bit different. Why? Because it will show this type of graph. You can't extrapolate this, right? You can't extrapolate this. So how you should calculate the limiting molar conductivity for them? You have to use the limiting molar conductivity for the strong electrolyte. Utilizing them, you can calculate the limiting molar conductivity for the weak electrolyte. That's the concept. So here you can see the conductivity of electrolytic solution at infinite dilution is called limiting molar conductivity. I guess it's clear. Next question, very important, state Kohlrausch's law. So here basically you can see it states that the molar conductance of an electrolyte at infinite dilution is equals to the sum of the ions of the conductances of respective cations and anions of the electrolytes. Okay, so basically what happens whenever you are diluting a solution infinitely? So initially if you just have taken, let's say 100 ml volume, and you have taken 50 gram of NaCl in it. Okay, so Na plus and Cl minus ions are so close to each other, so close to each other that they are not having individual contribution towards the conductivity. They are influenced by the surrounding ions. But whenever you are diluting it so much, then let's say you have diluted it 50 times or 100 times. So one Na plus is here, another Na plus is here, one Cl minus is here, like that. So they can travel or they can migrate independently, right? So they have individual contribution towards the conductivity, right? So these particular thing that they have individual contribution towards the conductivity whenever you are diluting it infinite times. This is called Kohlrausch's law. Okay, I guess it's clear. That's why all the cation, all the anion we will take. That's why the sum of all the cations and all the anions. I guess it's clear to you. Let's proceed. Here you can see example is given here. So if you are just looking at the Na plus and Cl minus, let's say sodium chloride, then lambda M0 will be the contribution of Na plus and Cl minus total. Okay, let's proceed further. Here you can see given application of Kohlrausch law. First application that I can tell that utilizing the Kohlrausch law, you can calculate the conductance of weak electrolytes. You can calculate the conductance of the weak electrolyte. Okay, like you can see, I am having the conductance of CH3CONA, sodium acetate, HCl and NaCl. Utilizing these strong electrolyte, I can calculate the limiting molar conductivity for the acetic acid. That's a weak electrolyte. Okay, next you can see the molar conductance of NH4OH at infinite dilution, that is a weak electrolyte, can be determined using the three strong electrolytes. Okay, so I guess you understood this. Utilizing a very strong electrolytes, because utilizing strong electrolyte you will get the graph from the Debye-Huckel equation, and by extrapolating you will get the limiting molar conductivity of the each ions, right? So utilizing those value you can put into the molar conductivity of the weak electrolyte, and hence you can calculate it. I guess it's clear. Let's proceed further. Here you can see, name the type of batteries or the commercial cells. So what you know, it is primary batteries and secondary batteries. Next question you can see, state Faraday's second law. Both the laws are very important, second law and first law. So as you can see, when same amount of electricity is passed through different electrolytic solution, the mass of the substance that is deposited or liberated at the electrodes, they are directly proportional to the equivalent mass. Okay, next is Faraday's first law. That is also very important, along with the mathematical abbreviation. You can see so many years it is repeated. So it is stated that the amount of substance that is deposited or liberated at any electrode during the electrolysis is proportional to the quantity of electricity passed through it. Okay, so W is directly proportional to the Q. Okay, next you can just remove the proportionality sign, because Q equals to I into T, you know. Remove the proportionality sign and W will be equals to Z into I into T. So make sure you are writing what is W, what is Z, what is I, what is T. So what is Z? Z is called electrochemical equivalent of a material. I guess it's clear. Let's proceed. Okay, explain the methods to prevent corrosion. You can use a barrier protection method, like you can apply grease, oil, color, electroplating, like this. Sacrificial protection means you can protect the surface by providing the layer of another metal on it. That is called, like utilizing zinc, if you proceed, it is called galvanization, right? Next you can see electrical protection also you can give, like this particular case what happens, iron is connected to a more active metal. Let's say we can connect it to magnesium. Okay, next anti-rust solution, like you can use bisphenol, you can use alkaline phosphates. This type of anti-rust solution also you can use that will prevent corrosion. I guess it's clear. Let's proceed. Here we will start the chemical kinetics chapter. So, order and molecularity, you know it's a very famous question. So, difference between order and molecularity. So, you can directly start with its order is an experimental value, molecularity is a theoretical value. Order is the sum of the power of the concentration terms, that is experimentally derived, and molecularity is the nothing, it comes from the stoichiometry. Right. Now you can see it is derived from the rate of the equation. Order can be 0, fraction, negative, anything, but molecularity is always a whole number integer, right? So I guess any 2 or 3 point you can take from here and you can make a note of it. Well, I guess it's clear to you. Let's proceed for the next question. So here you can see in a chemical reaction, A plus B gives C plus D. The concentration of reactant A alone is increased by 2 times, the rate is increased by 4 times. If concentration of both A and B are increased by 2 times, the rate is increased by 8 times. What is the order of the reaction with respect to A and B? Let's do it. So, at first let's write the general rate equation. Let's say K of A power X into B power Y, let it be equation number 1. Next they are saying if let's say A is increased 2 times, so 2A power X, B power Y, let it be 4 times, 4R, fine. This is equation number 2. Next you can see if you increase both by 2 times, right, so you can make it 2A power X into 2B power Y, that is basically 8R, right, it is increased by 8 times. So this is my equation 3. So we made 3 equations. Now what do you have to do? We have to divide this equation in such a way so that the similar terminology gets cancelled out and we can solve, we can get the value of X and Y, that's it. So let's do 3 divided by 2. So if you do this, then 8R is basically equals to K into 2A power X into 2B power Y divided by 4R, and here I am getting K into 2A power X into B power Y. So cancel out K, 2A, everything will be cancelled out here. You can see R will be cancelled out, hence I am getting 2 here, and that side I am getting 2 power Y. By comparing the power, we can get Y equals to 1. Okay, now let's calculate the value of X out there. So what you can do is you can simply divide 2 divided by 1, right? 2 divided by 1. Okay, so I am having 4R equals to K into 2A power X into B power Y. Here I am having divided by R. Here I am having K into A power X into B power Y. Fine. So from here B will be cancelled out, and from here I am getting 4. 4 equals to 2 power X. So from here I can compare the power. So from here I am getting X equals to 2. Okay, so my final equation is going to be R equals to K into A power 2 into B power 1. So the reaction is second order with respect to A and first order with respect to B, and overall order, it is overall order if you want to find, it is basically 2 plus 1, that is 3. It is a third order reaction. I guess it's clear to you. Let's proceed further. Okay, what is pseudo first order reaction? Another short question and with example. So pseudo first order reaction is basically a higher order reaction that can be converted to first order reaction by changing the experimental condition. So basically if any one of the reactant is present in a high amount, higher excess, then the second order reaction actually it behaves like a first order reaction. Okay, it's not a first order reaction, but it behaves like a first order reaction, and hence it is called as pseudo first order reaction. So you can take the example of hydrolysis of ester or inversion of cane sugar. Any one of them, you can just write down the example. I guess it's clear to you. Let's proceed further. Write the Arrhenius equation. State as to what the symbols stands for. So here comes the Arrhenius equation, K equals to A into e power minus A by RT. Please don't forget to write down the abbreviation. Okay, here A is a frequency factor or pre-exponential factor or Arrhenius constant, anything you can write. Rest of the thing I guess you know. I guess it's okay. What are the main criteria for the effective collision according to the simple collision theory? So here you can see, you can just take the name of the orientation. Proper orientation is mandatory, and activation energy. The energy barrier needs to be covered. These two. Let's proceed. Here we are going to start with the D and F block elements. So let's proceed for the D and F block element. So here comes the first question: why zinc, cadmium and mercury are not regarded as transition elements? So basically they are D block elements and they have their D orbitals filled with electron. All of them are having D10 configuration. So whenever there is D10 configuration, how the electron will undergo transition, you tell me. So there is no chance of transition, and hence they are not considered as transition element. I guess it's clear. 3D series transition metals exhibits +2 as the most common oxidation state. Why? So the reason is basically the 2,4s electron that can be eliminated easily, right? But if you just look for the scandium is having basically 3d1 4s2. So after removing the 4s2, if the 3d1 electron is also removed, then you will get the P6 configuration, that is a noble gas-like configuration, and hence that becomes very stable. I guess it's clear. Name the element of 3D series which shows maximum or highest oxidation state. So definitely that's gonna be manganese. Very important zone of question. Few more things that I wanna tell, that highest oxidation state of manganese +7 is exhibited by the compound with oxygen only. Okay, the reason is oxygen can form multiple bonds. It can stabilize the complex by forming p-pi bonding. Okay, whereas fluorine, if you just talk about fluorine, the fluorine also can, you can just think of an like alternative option for it, but fluorine can't form multiple bond, right? So remember this point, one extra additional point I just discussed here. Let's proceed. Name a transition metal which does not exhibit variable oxidation state. That is going to be zinc. Definitely it's having only option that is 4s2 electron will be eliminated and it will be D10 configuration, right? Very stable, full field stability. Calculate the spin only magnetic moment for the M2 plus ion. Okay, so basically what you have to find, you have to find out the number of unpaired electron for this, and then you have to put it into the formula. You have the formula under root n into n plus 2, and like that you can proceed. Here you can see, if you just draw the electronic configuration, they told that Z equals to 27. So with respect to that, M2 plus ion will be 3d7 configuration. Hence I am having 1, 2, 3 unpaired electron, right? So now 3 n value is 3. Put the value, calculate, it will come as 3.87 bone magneton. Make sure you are writing the unit. Very important. Even if you have done the full thing, they will cut 1 mark. So don't let them cut your marks. Let's proceed further. Zn2 plus salts are colorless. Why? Again the same question, from the same point of view. Zn is not having any kind of unpaired electron, right? D10 configuration. So Zn2 plus means D10 configuration. It has no unpaired electron, hence no D to D transition. Why color comes? Because of the DD transition, right? So there is no transition, hence no coloration. So I guess it's clear. Let's proceed. Cu2 plus salts are colored. Give reason. So basically the presence of unpaired d electron that will undergo D to D transition, and hence it will give you the colored. Okay. It's clear, I guess. Let's proceed. Explain the catalytic properties of the transition metal. Very important question. So basically, why? First is variable oxidation state, large surface area. Why large surface area? Because if I have large surface area, I can let the reactant molecule sit on the surface and the reaction will proceed. Okay. And partially filled d orbital. Important thing, and formation of a very stable intermediate. Okay, that makes the activation energy lower. Okay, few example that you can just give, like vanadium pentoxide. You can give the example for that is used for the contact process, right, for the manufacturing of the H2SO4. Like this type of example you can give. Let's proceed. Here we will start with the coordination compound. So first question here is what are ambidentate ligands? So ambidentate ligands, they basically have two donor atoms in them, but they donate from one atom at a time. One donor atom at a time. Let's take an example. Please make sure whenever you are facing this type of question, don't forget to give the example. Okay, you can give the example of cyanide, you can give the example of thiocyanide, nitrate, anything. Fine. So here you can see Cn minus, that is donor site is carbon, that is called cyanido. But if the donating side is nitrogen, it is called as isocyanate. Okay, another example I can take this. This is thiocyanate when S is donating, but whenever nitrogen is donating, it is isothiocyanate. I guess it's clear to you. Let's proceed further. Homoleptic and heteroleptic complex, both of them are important. Homoleptic complexes are those complexes in which you are having same type of ligand inside the coordination pair with a same metal. And heteroleptic complex, whenever you are having different type of ligand inside the coordination entity. Let's see. This is the example. You can see nickel with 4 carbonyl. I guess it's clear. Here you can see this is the heteroleptic complex. Here comes the example. I guess it's clear to you. Let's proceed further. What is ionization isomerism? Give an example. So ionization isomerism means the overall molecular formula definitely is going to be similar, but the ions that it will produce will be different. So here you can see complexes having the same molecular formula, but they give different ions when they are dissolved in water. So here you are having Br minus as an ion, but here you are having Br inside SO4 2 minus as an anion. This is an example. Here comes another example as well. You can see. I guess it's clear to you. Let's proceed further. Write a note on geometrical isomerism. Very, very, very repeated question, I guess you can see. Okay. So geometrical, why it comes? Definitely my compound must be heteroleptic. Okay. So geometrical isomerism, first definitely it should be heteroleptic complexes. Okay. Next, they occupy the position either at the same side or at the opposite side. Because of that only it comes. Okay. Usually with the coordination number 4, this type of complex we observe. Okay. So now here you can see geometrical isomerism is exhibited by this type of complex MX2L2. Some octahedral complexes as well. You can see MX2L4, MX3L3. Okay, so this is one example. We can see cis and trans isomer out of it. But sometimes what we can see is, for this type of example, here you can see MX2L2. If you just see here also, you can see cis trans isomerism. And if you just have this type of compound like ABXL, means all different type of ligand. So geometrical isomerism is also possible like this, cis and trans for this type of element. Here you are having ethylene diamine. Ethylene diamine means it's a bidentate ligand, right? It's a bidentate ligand, and here Cl2. So both the ethylene diamine same side, it is cis, opposite side they are trans, right? So now if they are cis, they exhibit optical isomers as well. Okay, so from the cis you can further draw another dextro and levo. That's a different case, optical isomers. Anyway, so here comes another thing, that is MA3B3 type of compound. If you are having MA3B3 type of compound, you can have facial and meridonial. Okay, facial means if you just connect these three same type ligand and these three same type ligand, they two plane will be connected and they will be facing parallelly. They will be facing each other, parallel to each other. But if you are like this, one plane is like that, another plane is like this, one plane is perpendicular to another, that is meridonial. Okay, I guess it's clear to you. Let's proceed. Here we are going to start with the organic chemistry, haloalkanes and haloarenes first. So here first comes the Finkelstein reaction. Here you can see we simply can take one alkyl halide in presence of sodium iodide and dry acetone. That will give you the alkyl iodide complex, okay, alkyl iodide compound. Okay, so here you can see ethyl chloride they have taken, and you can use sodium iodide and dry acetone to give you the C2H5I. So halogen replace. Okay. So here you can see addition of dry acetone precipitates formed NaBr and NaCl to prevent the backward reaction. Okay, it's a one important point that is given over here. You can just make a note of it or you can avoid it. Here you can see next it's Schwarz reaction with example. Here you can make the fluoride compound. So Rx, any kind of X can be changed with fluorine. So here we use silver fluoride, or sometimes cobalt trifluoride also you can use. Okay, that the halogen will be replaced with fluoride. I guess it's clear. Let's proceed. Give two differences between SN1 and SN2. Very important question. First is unimolecular, that one is bimolecular. This is first order kinetics, that is second order kinetics. Here you can write the rate, in which case the reactivity is maximum 3 degree, then 2 degree, then 1 degree, then a normal methyl halide. Okay, why? Because it proceeds through carbocation intermediate, and that doesn't proceed to carbocation intermediate, but rather steric factor takes over there. I guess it's clear. One more important point, you can just make a note that product obtained is a racemic mixture. Okay, both R and S you can expect, and for that case there are inversion in configuration. If you start with the R, you will end up with S. That's it. Let's proceed further. What is a racemic mixture? Okay, so it is basically equimolar mixture of the dextrorotatory and levorotatory isomers of the racemic, is called racemic mixture. So what is dextro and what is levo? Basically, if you are having an optically active compound, optical activity is an experimental thing. Okay, if you are just putting your compound inside a polarimeter, if it can rotate the plane of polarized light, then it is optically active. If it rotates the polarized light clockwise, it is dextro. If it rotates the polarized light, plane of polarized light anti-clockwise, then it is levo. So you will get the mixture of dextro and levo. Like you can see the example, it is denoted by plus minus sign, like plus minus lactic acid or DL lactic acid you can write. I guess it is clear to you. Let's proceed. Wurtz-Fittig reaction. So here comes the Wurtz-Fittig reaction. So basically here you are having one Rx, one alkyl halide and one aryl halide. So that alkyl group and aryl group, they gets connected. Okay, I guess it's clear to you. Here you can see one bromobenzene taken as example in presence of sodium, and one bromomethane is taken. So you will get toluene out of it, methyl benzene. It's clear, I guess. Here you can see Fittig reaction with example. So that is basically it is something that we use to prepare biphenyl or diphenyl type of compound. Okay, aryl halide you have to take in presence of sodium, 2 units of that you need, and you will end up with diphenyl. I guess it's clear. Let's proceed. Here comes alcohols, phenols and ethers. So the first question, what is Lucas reagent? Very important question. And how would you distinguish and distinguish an alcohols by using the Lucas reagent. So Lucas reagent basically is ZnCl2 in presence of HCl. So basically if you are having 3-degree alcohol, then in presence of Lucas reagent you will get immediate turbidity. Okay. If you are using 2nd-degree alcohol, then with this Lucas reagent you will get turbidity after 5 minutes. So once you are getting turbidity after 5 minutes, you can identify it as a 2-degree alcohol. Let's say you are not getting any turbidity at all in normal temperature, you have to heat and then you will get some turbidity, then you can ensure that it's a 1-degree alcohol. I guess it's clear to you. Let's proceed. Okay, explain Cole's reaction. How do you convert phenol to salicylic acid? Very important question. You can see so many years this question have been repeated. So here you can see, so you are having a phenol, you have to make the sodium phenoxide, and then from that if you just give carbon dioxide in some pressure and temperature, then it will end up with the salicylic acid. Okay, very important reaction. Please make sure that you are doing it, you are remembering it properly. Sometimes I have seen people, they are messing up in between Cole's reaction and Raymer-Timmons reaction. Please don't do it. Okay. Let's proceed. Here comes Raymer-Timmons. Fine. Here you can see Raymer-Timmons actually salicylaldehyde. Okay. So from phenol only you have to start. You have to treat it with chloroform in presence of aqueous NaOH, then it will form some intermediate compound and then further NaOH, okay, and then you can just end up with salicylaldehyde. Okay, I guess this is a name reaction direct question. I guess it's clear to you. Very important, both of this. Let's proceed. We will proceed with now aldehyde, ketones and carboxylic acid. So here comes the first question, how would you prepare aldehydes from the esters? So you can use definitely dibyl H, diisobutyl aluminium hydride. Okay, this is a very good very good hydride provider or reducing agent that can reduce this ester group to the aldehyde. Okay. So next question, you can see name the reagent or oxidizing agent used for the etard reaction, that you know it's chromyl chloride, that is CrO2Cl2. Very important question, please remember that. You can expect this question in the MCQ as well. Next you can see what is etard's reaction, explain. So here you can see if you are having methyl benzene, then in presence of chromyl chloride you will get some chromium complex. If you further hydrolyze it, then you will end up with benzaldehyde. That is your etard's reaction. Proceed further, Gatterman-Koch, very important GK reaction. So from here basically from benzene directly benzaldehyde you can get. So what is the reagent? Carbon monoxide in presence of HCl and some anhydrous AlCl3 we need as a catalyst. So this is your GK reaction that will give you the benzaldehyde. Next you can see, explain the mechanism of nucleophilic addition reaction of aldehydes and ketone, important one. So basically what happens, it's a planar molecule, carbon monoxide is a planar molecule, so nucleophile can approach from the up or from the bottom. So let's say if it is approached from the up, so this bond will be opened and nucleophile will get attached on the carbon and it will form a tetrahedral intermediate. Okay, it will form a tetrahedral intermediate. Further, it will release it will takes up one H plus, and that particular process is going to be very fast. Here you will end up with H. I guess OH over there. I guess it's clear. So basically the question comes with respect to cyanide addition or HCN addition in C double bond O in carbonyl. We will see. I guess it's clear to you. So most important thing that you have to explain properly, from sp2 hybridization, this carbon is basically here sp2. Okay, from sp2 hybridization, the intermediate and the addition product, ultimately you are ending up with a sp3 hybridization. Okay, remember that. Let's proceed. Aldehydes are generally more reactive than that of the ketone. Two reasons we can discuss over here. One is steric effect, another one is electronic effect. Why steric effect? So basically if you are using ketone, Okay, two R groups are there, two R groups. So if nucleophile wants to approach the carbonyl carbon, then it needs some space. That attack must be prominent. If the two bulky R groups, they prevent the approach of nucleophile towards the carbonyl carbon, then definitely the reactivity decreases, and hence ketone is less reactive than that of the aldehyde, because in aldehyde one end is hydrogen, right? Next one is electronic effect. So basically in this is my ketone, right? So I'm having 2 plus I effect having group. So plus I effect, what it does, it gives the electron supply to the central carbonyl carbon, right? It gives, with the plus I effect, it donates the electron towards the central carbon. As a result of this, the electrophilicity of the carbon reduces, right? The electrophilicity of the carbon reduces. Why the nucleophile will attack? If the carbon is not electrophilic, right? But here in case of aldehyde, you are having only one CH3 group, comparatively lesser effect, right? So for this reason also you can say ketone is less reactive than that of aldehyde. I guess it's clear. Let's proceed. Explain the mechanism of addition of HCN to aldehyde or ketone. One of the most important thing, they can directly ask you the question, the nucleophilic attack, or they can give you this HCN wala example. Okay. So the approach is going to be similar. You can see HCN in alkaline medium, it produces Cn minus. Cn minus is your nucleophile. So Cn minus, it can approach from the top end or it can approach from the bottom end, right? So once it will approach over here, it will form some tetrahedral intermediate over there, then proton transfer will take place, and the most importantly, you will end up with a compound that is called cyanohydrin. Okay, so that particular transition you can expect whenever carbonyl is treated with HCN. I guess it's clear to you. Let's proceed for the next question. How do aldehyde and ketones react with NaHSO3? Give an example. So basically here you can see a very important zone. Okay, so sometimes indirectly they ask the question out of it, like they can ask you the question like, how can you separate aldehyde from the mixture of aldehyde and ketone? Okay, very important thing. So here you can see carbonyl, if you react with sodium bisulfate, it forms this type of compound by proton transfer. Here you can get this type of bisulfite addition compound, and it is water soluble and it can form the crystal, right? So here aldehyde is more reactive towards it. Okay, aldehyde is more reactive towards it because you know aldehyde is more reactive than that of ketone. So aldehyde will react with this particular compound faster, and it will make this compound that we can filter out, right? That we can filter out, and in the filtrate we will be having the ketone. So further from here, if you just give some dilute alkali or dilute acid, then your aldehyde will be back. Okay, so this is a separation technique. Actually, it's a nucleophilic addition. Let's proceed further. What is a Clemmensen reduction? Be careful, the reaction may not come directly, it can come directly as well, or else you can expect the question related to it, that what is a reagent that is used for the Clemmensen reduction. Here you can see I am having one carbonyl group, I am using zinc amalgam in concentrated HCl, and I will end up with hydrocarbon. I guess it's clear. Wolff-Kishner, again I am telling the reagent is also important, so here actually we use hydrazine, right? So here you can use the hydrazine, and definitely you will again end up with the hydrocarbon over here. I guess it's clear to you. Let's proceed. Here we will start the amines. Yes. So first question, you see so many years it is repeated. Hofmann-bromamide reaction. So Hofmann-bromamide reaction, what basically happened? You are having one amide in presence of alkali, that is NaOH. You can end up with primary amine. Okay, that's it. Let's proceed for the next question. Here you can see, what is a carbylamine reaction? Very important, super important question. So basically what happens, if you are having primary amine, it is a test to identify if you are having the primary amine or not. So if you are having primary amine in presence of chloroform and KOH, okay, you will end up with a foul smelling compound, that is a isocyanide. Okay, if you are getting that smile, that is a, if you are getting that smell, not the smile, sorry. I know so many of you are smiling right now, it's fine. Okay, so if you are ending up with the NC or a foul smelling compound, then you can tell that yes, I started with a primary amine. So this is a test. Okay, so I guess it's clear. Let's proceed further. What is a Hinsenburg reagent? How do you distinguish between 1 degree, 2 degree and 3 degree amines using the Hinsenburg reagent? So very important question, super duper important question. Directly they can ask only the part question like what is Hinsenburg reagent? That's enough. So this is basically benzyl sulfonyl chloride. Okay, so basically what happens, benzene sulfonyl chloride, if it's react with primary amine, you will be getting some compound that is soluble in alkali. Okay, then you can tell that okay, I am having primary amine. Okay, next, benzene sulfonyl chloride, if it is reacting with some amine and you are getting some compound that is insoluble in alkali. Okay, then you can tell that okay, I am having 2 degree. Fine. Further, if you are having if you are reacting with the Hinsenburg reagent but it is not giving you anything at all, no reaction takes place. Okay, then you can tell that I am definitely having a tertiary amine compound. Like that you can identify 1 degree, 2 degree and 3 degree amine. I guess it's clear to you. Let's proceed. Here we will start up with the biomolecules. So very important, reducing sugars and non-reducing sugars along with its example. So reducing sugars means those sugars they have in the open chain form, they have one aldehydic unit, okay, and they can actually reduce the Fehling's Tollens or Benedict reagent. Okay, so you can take the example of glucose, fructose, maltose, anything. Okay, they have the free aldehydic group that actually does the electron transfer, means reduction. I guess it's clear. Then next, non-reducing sugar, any one of them you can expect in your examination. So definitely here basically cannot reduce the Fehling's and Tollens due to the absence of the aldehydic unit. Rather, it is adjacent to some alcoholic unit. Okay, let's say sucrose you can have. Okay, let's proceed. Very important question. Like better to say that entire structural analysis for the glucose is very important. Okay, among them these are the most repeated question that I have figured out here. So here you can see how does glucose react with the hydrogen iodide, or how do you show that glucose contains 6 carbon in a straight chain. So if you just heat that glucose in HI in presence of red phosphorus, you will get a chain of 6 carbon. So that will tell you yes, my glucose is containing 6 carbon. I guess it's clear to you. Next, this one is also very important. So how does glucose react with hydroxylamine, or how do you show that glucose contains carbonyl group? So basically if this particular glucose it reacts with hydroxylamine, it forms glucose oxime. Okay, that will tell me that yes, glucose contains one carbonyl group at the top. I guess clear to you. Proceed further. What are the anomers? So anomers are basically if you are having, like if the sugars, if it differs with respect to C1 configuration. Okay, if you just look at this particular case, this is the anomeric carbon. Here with respect to C1 the OH is below, here it is up. Okay, this is alpha, this is beta, right? Pyranose, this is alpha D pyranose, alpha D glucopyranose, and this is beta D glucopyranose. OH is below, OH is up. So if the structure differs with respect to carbon 1, then it is called anomers. Next one is also important, epimers. If it changes with respect to any carbon rather than that of carbon 1. If with respect to carbon 1, that is anomer. If it is any carbon rather than that of carbon 1, then it is epimer. Okay, I guess you can see it is D-glucose and it is D-galactose. You can see this carbon. Okay, here you can see with respect to this carbon there have different configuration, carbon 4. Okay, carbon 4 is of different configuration. I guess it's clear. Name the optically inactive amino acid, very important, alpha amino acid, that is the you can see glycine. This is the structure of glycine. I guess it's clear, very important question, remember that. Next you can see how can you form the peptide bond, and you can see if I am having one carboxylic acid unit and here the amine end, okay. So here basically from that 1 unit of water gets released, okay. 1 unit of water gets released. As a result of this you will get the dipeptide, that is CONH, it will form here. I guess it's clear to you, that is a peptide linkage, okay. Next you can see how are proteins classified on based on structure and molecular shape. So here you can see fibrous protein, globular protein. In the model paper question you can see the question that they are asking only for the example. So this particular zone is important for you. So one is fibrous protein, you can take the example, one is globular protein. So fibrous protein means it is a structure that is fiber-like structure, insoluble in water, okay. You can take the example of our hair, that is a keratin protein or collagen, or the muscle protein, that is a myosin, right. That you can take the example. And here if you are having globular protein, they are actually spherical shape, and they are soluble in water. Like you can just take the example of insulin, albumin, hemoglobin itself, okay. I guess it's clear to you. Let's proceed. Name the protein present in your hair. You know better than me. So I guess it's okay. I guess you people go for the keratin treatment and all. So before you are studying the biomolecules, you are known to this compound, right? Let's proceed. Here we will discuss with some miscellaneous problems along with some numericals with different chapters. So let's proceed with the first problem. Okay. So here you can see, looking at the problem, it feels it's a solution chapter. Okay, the boiling point of benzene is 353.23 Kelvin. Okay, when 1.8 gram of non-volatile solute was dissolved in 90 gram of benzene, the boiling point is raised 354.11. Calculate the molar mass of the solute, Kb is given. Direct question, okay, elevation of boiling point you can directly apply. So what I will do at first, let me just write down the formula. The formula is basically, let's say molecular weight of B is basically Kb into Wb into 1000 divided by delta Tb into Wa, right. Delta Tb, let's calculate. Delta Tb, if you want, that is definitely Tb minus Tb0, right. So that's going to be 354.11, 354.11 minus 353.23 Kelvin. So that's going to be, just a minute, I'm not a human calculator, I'm so sorry for that. You are going to get 0.88. Okay, because in the board examination definitely you are going to get the calculator, so please don't expect me to do the addition and subtraction also in the with my own mind. Okay, so yeah, definitely in some other video I will tell you the numerical trick and tricks if you stay tuned, and if you don't forget to like, share and subscribe. So you will get those informative videos as well, where I will tell you the hacks, the tricks by using which you can just like this you can do the numerical problem. Okay, so as of now use your calculator. Yeah, so now here you can see, let's put the value of Kb, that is 2.53 into, okay, just a minute, I have to calculate Mb, right. Weight of B, that is 1.8 into 1000, okay, divided by, this is 0.88 into, I'm having 90 gram of benzene. Okay, so if you calculate this, you will end up with 58 gram per mole. I guess it's a direct question, it's clear to you. Let's proceed for the next one. Here you can see, write the Nernst equation and calculate the EMF of the following cell. State whether the cell is feasible or not. Okay, so better at first write the reaction, then we will proceed one by one step. Okay, so let's write the reaction at first. So I am having 2, okay, Br minus plus let's say 2H plus will give you Br2 plus H2. Okay, so from here N you can expect it's going to be 2 electron. Fine. Now let's put this thing into the Nernst equation. So what is your Nernst equation? It is basically E cell equals to E0 cell minus 0.059 divided by N value is 2 here, log of, see these and these both of them are in elemental state, so we will not take them, we will take this. So Br minus whole square and H plus whole square. Right, I guess it's clear to you. Okay, E0 cell also I have to calculate. So E0 cell, I guess you know that is cathode minus anode. So that's going to be that side minus this side. So for hydrogen it's going to be 0 minus this 1.09. So it is overall going to be minus 1.09. Okay, let's put the value over there. It's going to be minus 1.09 minus here. This particular case, let's put the value here, 0.059 divided by 2 log of 1 divided by concentration of Br minus, right? That is 0.1 whole square and H plus is 0.03 whole square. Okay, let's calculate. Let's make it simple, then you will get the answer, nothing else. 0.9 minus 0.059 divided by 2. From here, if you just calculate, it will come as 9. So 1 divided by, from here comes 10. Okay, 1 by 10, 1 by 100. Okay, so from here you will get 9 into 10 power minus 8, 2 square into 2 square means 4 into 2. Okay, 9 into 10 power minus 8. Fine. Next, minus 1.09 minus 0.059 divided by 2. 1 by 9 if you do, it will come as log 0.11, like that it will continue into 10 power 8. Okay, let's proceed. Then minus 1.09 minus 0.059 divided by 2. From here I can do it like log 0.11 plus log of 10 power 8. Okay. From here, okay, this particular thing I can do a little bit simplification, then log calculation will be easier. So this thing, just a small change, you can see, I can do it as 1.11 and 10 power 7, right? So here log 1.1 it will come into, plus log 10 power 7 plus log 10 power 7. Okay, let's calculate then. Minus 1.09 minus 0.059 divided by 2. Here you will get log 1.1 value, you will get almost like 0.0457 plus 7. Okay, now if you just calculate the entire thing, I am not going in depth because I already showed how to just break down the log. I can directly come up with the answer. So you will get it as minus 1.0292 volt. Okay, that's going to be your answer. Okay, now one part question is there, state whether the cell is feasible or not. Basically delta G equals to minus NF E cell. Okay, from here you can just get the hint, if E cell value is positive, then only it is possible that the del G value comes negative, and hence you are getting the spontaneous reaction, right? Your E cell value should be positive, but here you can see your E cell value comes negative, right? So negative will make positive, hence del G value is positive, means it's a non-spontaneous process. I guess it's clear to you. Let's proceed further. Okay. Judging by the question, it seems like it's from Kohlrausch law. So yeah, calculate lambda m0 for CaCl2 and MgSO4. Given that lambda 0 for Ca2 plus is this, Cl minus is this, Mg2 plus is this, SO4 minus is this. Okay, chalo. Let's put the value over there and we can calculate using the Kohlrausch law. So basically we have to calculate lambda m0 for CaCl2. So that is basically lambda 0 for Ca2 plus lambda 0 for 2Cl minus, right? So from here I can proceed with Ca2 plus value is given. Yes, 119.0 Simon centimeter square mole inverse. Okay, plus 2 into 76.3 Simon centimeter square mole inverse. Okay, so if you calculate this, it will come as 266 Simon centimeter square mole inverse. That's going to be your answer. That's it. I guess it's clear. Okay, so this is for CaCl2. We have to calculate again for the MgSO4 as well. So lambda m0 for MgSO4. If you calculate, so it will give you lambda 0 of Mg2 plus lambda 0 for SO4 2 minus. So for Mg0 the value is given 106 plus here you are giving 160 Simon centimeter square mole inverse, right? So from here you will get 266 Simon centimeter square mole inverse. That's it. I guess it's clear for you. Let's proceed. Here you can see our first order reaction takes 69.3 minutes for 50% completion, means T half value is given. Okay, how much time it will be needed for 80% completion? Okay, very nice question, very easy question. So we know the formula of T half, that is 0.693 divided by T half, right? So that is basically K will be 0.693 divided by 69.3. From here I will get 0.01 minute inverse, right? Let's put the value of K in first order kinetics. K equals to 2.303 divided by T equal into log of let's say R0 by R, right? R0 by R. So from here I can take T equals to 2.303 divided by K value. From there I can write T of 80%, okay? 0.01 log of R0, so we can take it as 100 divided by, if 80% is completed then 20% will be left out, right? So if you just simply calculate the time in 80%, it will be coming as 0, I am cancelling out, 2.303 divided by 0.01 into log of 10 minus log of 2, right? So from here, or else log 5 directly you can do, actually it will be even easier for you. So let me just do log 5 directly. So you can put the value T of 80% over here, that is 2.303 divided by 0.01 into log 5 value is 0.7, you can write actually 0.69 something it comes. Okay, so the value will come as 160.979 minute. I guess it's clear to you. Direct question it was. Let's proceed further. Okay, the first order rate constant for the decomposition of ethyl iodide is given. The activation energy is given. Calculate the rate constant at 700 Kelvin. So these actually you have to proceed with the Arrhenius equation, right? So yeah, let's proceed. Log K2 by K1 equals to EA by 2.303 or T2 minus T1 divided by T1 into T2. Okay, so let's proceed further. Log of K2 I have to calculate. K1 is given as 1.6 into 10 power minus 5. Here activation energy is also given, that is 209. We will convert it into joule into 10 cube divided by 2.303 into 8.314. Okay, here I have given the value 600 into 700 and here 700 minus 600. This is the calculation that you have to proceed with. Okay, so if you just do these calculation, log K2 by 1.6 into 10 power minus 5, if you do the right side calculation, you will get something 2.5989. Okay, now if you just do the anti-log, K2 divided by 1.6 into 10 power minus 5, anti-log means 10 power 2. Let's say 6. Okay, so 10 like this type of calculation, how you should proceed, you know, if you are having 10 power 2.6, so this particular thing you can proceed like 10 power 2 plus 0.6, hence from here 10 square plus 10 power 0.3 whole square. Okay, so now here actually you can put the value, there is a value of 10 power 0.3 that you can put here and you can square it. That is a rule actually. You can proceed like that as well, or else you can use your simple log table. Okay, so if you just calculate this thing, it will come as, and calculate and then multiply this thing, it will come as, K2 will come as 6.352 into 10 power minus 3 second inverse. I guess it's clear to you. There is no doubt. Let's proceed further. Okay, here comes one question, that is the preparation of potassium dichromate manufacture. So many years it is repeated, 3 marker question you will get out of it. You have to start with chromite. Okay, so chromite is treated with sodium carbonate in excess water, sorry, excess air. Okay, it will form sodium chromate. After that, that yellow solution is filtered in the acidic medium, that is H2SO4. You will end up with sodium dichromate. Then this sodium dichromate is heated with KCl, you will end up with potassium dichromate. Very important question. So many years it is repeated. Next you can see preparation of potassium permanganate is also very much important. So here you can see 2-step reaction, MnO2, at first you have to fuse with KOH and O2, you will end up with K2MnO4. Further this MnO4 2 minus means K2MnO4, if you just treat it with acid, it will give you MnO4 minus and MnO2. I guess it's clear to you. Let's proceed. Here you can see indicate the types of isomerism exhibit by the complex. Draw the structure. Okay, so for this particular type, what you can do is, for this type of thing, it is a bidentate ligand, right? So cis-trans isomerism definitely you will observe over here. Okay, so this is basically chromium, that should be chromium. Okay, just a small typing mistake. It's a chromium H2O whole twice, C2O4 whole 2. Yes, let's proceed. So chromium, if that particular oxalate, I'm just writing it like that normally, if that oxalate is of two opposite side, and here I am having one H2O, here I am having one H2O, this is my trans. Okay, now if I want to draw the cis, so this is my oxalate, this is my oxalate, okay, here I am having, let's say, H2O, and let's say here I am having the H2O. Okay, so this is my cis. Okay, now this cis can exist in two optical isomers, one is dextro, one is levo. So let me just make one mirror and let's draw the mirror image of it. So H2O here, H2O here. So if it is D, then that's going to be L. So this is how you can represent them. I guess it's clear to you. Let's proceed. Explain the crystal field splitting in octahedral complexes. So here you can just draw this diagram. So d orbital in crystal field, at first they comes close to each other because of the Coulombic interaction. After that, when they comes in crystal field, then repulsion they faces, the electron repulsion between the ligand electron and the metal d electron. Okay, as a result of this, when they finally approach the metal, when they finally attack on the metal orbitals, then they get splitted. Okay, two orbitals they gets of higher energy and 3 orbitals they gets lower energy. 2 orbitals dx square y square and dz square, they are called Eg together and they are called T2g, that is dxy, yz, dzx. And in the middle the energy gap is called crystal field splitting or octahedral splitting here, octahedral splitting energy. From the middle, this particular line is called barycenter. Above barycenter, the amount of energy is 3/5 del O. Below barycenter, it is minus 2/5 del O. Minus sign indicates the stability. Hi guys, it's clear to you. Let's proceed. The entire thing is explained. You can just take a snap, or better, don't go for the shortcut method. Yes, please make a note of it. Let's proceed further. Here you can see, explain the mechanism of SN1 reaction. Okay, so many years repeated question you can see. Let's proceed further. Here you can see, let's say I'm having a tertiary butyl bromide. Here I'm giving some alcohol. Okay, so first what will happen, first step is very slow because here my intermediate will be formed. So intermediate for this type of reaction, for SN1 type of reaction, is carbocation. So carbocation intermediate will be formed. Then what happened, then next step is very fast. Then once the carbocation is formed, then OH minus, that is the nucleophile, will attack over here and we will get the alcohol. Here that you have to mention, the first step is rate determining step. Okay, I guess it's clear to you. Let's proceed further. Explain SN2 mechanism, that is also very much repeated. Okay, so here you can see, let's say you are having one methyl chloride, this type of compound, and here you are having a leaving group. Nucleophile Cl is here leaving group. So basically when OH minus will attack on the carbon, you will come up with a penta-coordinated transition state. Okay, this is a transition state. That is neither the leaving group left nor the nucleophile it gets attached. Okay, so this is a penta-coordinated transition state. After that, any one of them they will leave, that is Cl will leave over there and OH will be permanent. Okay, and you will end up with the inversion in configuration if you start with a chiral or optically active molecule. I guess it's clear. Here you can see, explain the mechanism of dehydration of ethanol. Very important question, ethanol to ethene. Okay, so this is your ethanol. First step is protonation, second step is carbocation formation, last step is deprotonation. Okay, so these 3 steps carries 1 marks each. And here you can see oxygen lone pair will take this H plus and it will form H2O plus. So actually this protonation, this H plus attachment, this basically makes this OH a better leaving group. Okay, then what happens, then this leaving groups leaves the system and it forms carbocation here. Okay, after that what happens, elimination of proton, that is deprotonation. This hydrogen carbon bond comes here and the 1 H plus gets regenerated, that will work here further. I guess it's clear to you. Okay, let's proceed. Cumin, explain cumin process for the preparation of phenol, cumin to phenol reaction. This tertiary butyl, or sorry, isopropyl benzene is called cumin. Okay, if you treat it with O2, then you will get cumin hydroperoxide type of compound. From there, if you just give a little bit acid, then it will proceed the phenol. Very important. Phenol along with acetone, very important reaction, remember that. Further, you can see, right, the Howard structure of the alpha D glucose. So any one Howard projection you can expect any structure. Okay, so here you can see for the glucose I have mentioned here, this is the alpha D glucopyranose, means 6-member ring. Okay, I guess it's clear. Next you can see, write the Howard structure of maltose. So this is the maltose. You can see one glycosidic linkage is there among this carbon 1 and carbon 4. So this is how it looks like, alpha D glucose and alpha D glucose. 2 units, they are linked with glycosidic bond. I guess it's clear to you. Yeah. That's it, my dear. I guess this particular portion has covered your entire syllabus 2 and 3 marker questions. Yeah, numerical may vary, but the zone from where I took the numerical, they will not change. You can expect the numerical from those region only. So yes, to get more such informative video, please don't forget to like, share and subscribe, and make sure you're watching the video till end. Thank you so much for your support. Thank you.